Good evening, sir.
Yes, Samira. What we did in last class?
So we did revision of hydrostatics.
Hydrostatics. I think I defined up to surface tension.
Yes,
No,
sir.
I think it was last Archimedes principle.
Yes, sir.
In both, you said yes, sir. No. Okay, so we have to start with hydrodynamics. Any doubt from the last part?
No, sir.
In hydrodynamics part, we have first term, it was Newton's law of viscosity. Law of viscosity. According to this, liquid flows in layer by layer structure in which each layer opposes its neighboring layer by a force which is called viscous force. So viscous force acting between layer of liquid will depend upon area of liquid times velocity gradient, that is change in velocity with respect to its width. So it would be dv by dy and some coefficient of viscosity eta, and since this particular force is opposing nature, so there will be negative sign with it. So it was a formula according to this law of viscosity. So next in this part, eta is called coefficient of viscosity, having unit Pascal second. So its SI unit will be Pascal second and its CGS unit will be poise. 1 Pascal second is equals to 10 poise. This Pascal second is also called Poiseuille PL. Now there may know anything related to this part, which is most important. Next, on the basis of this behavior, we may define types of flow of liquid. So you will be asked to describe different flow of liquid. So we have mainly 3 different types of flow of liquid, that is streamline, laminar, and turbulent. Samira, just explain streamline.
In streamline liquid, the liquid should be non-viscous
Yes, further.
and incompressible.
Incompressible, okay. Is there any viscous force in this part? So you'll say no, it should be non-viscous first. Non-viscous, incompressible, and irrotational also. So that at a particular instant, velocity of each layer of liquid will be same. In case of laminar, there will be some viscous force in between layer of liquid. And in turbulent, there will be also viscous force, but as in this part, there will be formation of eddies that will term as turbulent flow. Now to define these different flow of liquid, we may define a number which is given by Reynolds. So it will be Reynolds number. Do you have any idea about this part? A formula related to this, how to calculate Reynolds number?
Yes, sir. It is rho Vd by no.
It is rho Vd by eta. So Reynolds number is rho Vd by eta. What is d here? Samaira, what is d here? D is diameter of tube in which liquid is flowing. We may transform this particular relation in other form in relation with Q, which is called a rate of flow of liquid, which is also equals to area of cross section times velocity. So you may substitute in place of velocity as Q divided by area of cross section. So it will be pi d square by 4. So this expression will become 4 times Q rho divided by pi d times eta. Further, you may write this particular expression as nothing but ratio of two different forces, numerator and denominator. For numerator part, we can say inertial force, and for denominator part, we can say viscous force. So Reynolds number is also a ratio of these two different forces. Inertial force means mass times acceleration, and viscous force due to flow of layer by layer structure. On the basis of this Reynolds number, we have assigned some specific value. If it is less than 1000, if it is in between 2000 and 1000, if it is in between 3000 and 2000, and last, if it is greater than 3000. So this is called streamline, laminar, unstable between laminar and turbulent, and this is completely turbulent. So on the basis of these different number, on calculation related to the flow of liquid in tube, we may assign its flow or type of flow. Samaira, any doubt?
No, sir.
Okay. Next is, in this part, we had viscous force between layer of liquid, which is defined by Newton. But suppose if a body is projected in viscous medium, so it must experience some opposing force, which is called viscous force again, which is defined by Stokes' law. So it will be viscous force experienced by body 6 pi eta r times v. In this expression, this entire part will be constant, 6 pi eta, coefficient of viscosity, r, radius of body. So it mainly depends upon this velocity of projection. So as velocity of body increases, viscous force on body will also increases. So this entire term from this point to this point is called damping factor, or quantity which is responsible for opposition of body if it is going through any viscous medium. So we can say this is B times V is equals to F with some negative sign since it is opposing in nature. So this B is called damping constant or damping factor. Now, using this concept, we may define another term that is called terminal velocity. Samira, could you explain what do you mean by terminal velocity?
It is the constant velocity with which a body is progressing in a viscous medium.
Good. So if body or if velocity of body becomes constant, so net acceleration and net force at that point will be zero, we can say. So F net will be zero, and similarly net acceleration will be zero. So terminal velocity will be 2 times of r square by 9 times of eta bracket sigma minus rho times gravity. In terms of mass, it will be m times g bracket 1 minus rho by sigma divided by 6 pi eta r. Now from this expression, there was a question, why helium balloon got halt after attaining some particular height? Samira, could you explain
So can you repeat the question?
why helium balloon after attaining some height got halt, get stopped? Why? Suppose if you release helium balloon or balloon filled with helium gas, so it will first go up in atmosphere or in air up to a particular height and get to stop there. Why? From this relation, we can say, according to density of medium and density of object, we may have 3 different cases. First, if sigma is greater than rho, if sigma is equals to rho, and if sigma is less than rho. In first case, if density of object is greater than density of medium, terminal velocity will be positive. It means it will be going downward. That is, it will be descending. In second case, if velocity of object and velocity of medium becomes equal, so terminal velocity will become zero. So in this case, there will be no any movement of that particular body upward or downward. And in third case, if sigma is less than rho, so terminal velocity will become negative. It means it will start ascending. So you will say, since in atmosphere, density of air will not be constant at all different height. So on increasing upward, density of air decreases. So at a particular height, when density of helium gas equals to density of air, so terminal velocity of balloon will become zero. That's why it got stopped there. Is it clear?
Yes.
Next, on the basis of this terminal velocity, may define combination of drops or raindrop or question related to those different parts. Suppose you have a number of individual drops which may be falling with some velocity v1. So if they are combined to form new drop having velocity v2. So what would be relation between v1 and v2? So from this expression, eta, rho, sigma, gravity, these all should be always constant. So it mainly depends upon radius. So we can say v1 by v2 is equals to r1 by r2 whole square. Just equate volume of these two different body and equating, you will get r2 in term of r1. So on solving, you will get v2 is equals to n to the power 2 by 3 times v1. Arslan, any doubt? Okay. Next is equation of continuity. According to conservation of matter, suppose if we have a tube having different cross-sectional area. Area at this instant is A1, this instant is A2. Since liquid is incompressible and non-viscous, so each layer will have same velocity V1 at this instant and same velocity V2 at this instant. According to conservation of matter, mass of liquid entering per unit time at this particular instant must equals to mass of liquid ejecting out at the other end. So Q is equals to area into velocity, which is equals to constant in this part. Q is called rate of flow of liquid. So we can say area times velocity must be equal, or amount of liquid entering per unit time must equals to amount of liquid ejecting per unit time. So if you will be asked to define graph related to these two terms, so we can say product of area and velocity is constant. It means area and velocity must be inversely proportional to each other. So graph will be rectangular hyperbola like this. So Myra, any doubt?
No, sir.
It is based on conservation of matter. Next is most famous part, that is Bernoulli's principle. Samira, just explain Bernoulli's principle.
For a non-viscous incompressible liquid, the liquid with no, the liquid should the sum of pressure, potential energy, and kinetic energy per unit volume should be constant at each instant.
Good. So we can say for flow of liquid in a tube whose end is at different height. So sum of pressure, kinetic energy per unit volume, potential energy per unit volume at any instant for the flow of non-viscous incompressible liquid is constant. What would be the limitation related to this Bernoulli's principle?
The liquid should be non-viscous and incompressible. Energy should be conserved and gravity should be constant.
Good. So we can say pressure plus half rho V square and rho GH is equals to constant. We may write this particular term in some other form also. Since in this part we have density, gravity, constant part, and only H is variable. So if you divide this entire expression, P divided by rho times G, V square divided by 2 times of G plus H. So again, it will be constant. So we may call this particular part, this particular part, and this particular part. First, this term is pressure head. This term is gravity head. Just 1 minute. Velocity head. And this is gravitational or gravity head. So from this expression, if I ask you, what would be the unit of this particular constant? Whether it would be unitless term or it will have some unit.
Unitless.
I defined you in second chapter, dimensional analysis. Principle of homogeneity, which state two different physical quantity can be added, subtracted, or equated only if they have same dimension, same unit. So if this is a quantity having pressure or unit of pressure, so this must also be in pressure, and this should be also in pressure. So the unit of this constant part will be Pascal. Is it clear?
Yes.
Similarly, in this expression, this is height, which is measurement of length, we can say. So its SI unit will be meter. So this constant will also have unit of meter. This term and this term will be same, that is meter. Is it clear?
Yes.
Okay. Now, on the basis of this Bernoulli's principle, you will be asked just to derive this expression. And next, on the basis of this part, you will be asked, first is Torres-Lee law, one of the application of Bernoulli's principle. In Torres-Lee law, I had defined you two different parts. One is for closed tank and the other is for open tank. You will be asked to derive for closed tank. Let me define you how to derive. Suppose if you have closed tank or open tank. In first part for closed tank, there will be pressure inside it at this point, and also pressure from outside atmosphere P0 at this point. So if you assume this particular part to be in the form of tube, like this, whose one of the cross section is at this point, at this point. So velocity of liquid at this instant will be approx 0, since it is very large as compared to this part. So only we may define velocity of ejecting liquid at this point, which is called velocity of efflux. So using Bernoulli's principle, height of this particular tank or up to which liquid is filled, a hole is cut out at this point. This is H minus H. So according to Bernoulli's principle, pressure at point 1, that is Pi, rho half rho V1 square and rho g h1 is equals to pressure at point 2 half rho v2 square and rho g h2, that is h minus h. This is 0. So on solving, you will get velocity of efflux, or velocity with which liquid is ejecting out from this particular hole, will be equals to root under 2gh plus 2 times pressure difference Pi minus P naught divided by rho. So this will be expression for this closed tank. But in terms of open tank, since at this point pressure will be P naught and also at this point pressure will be P naught. So if you're assuming this particular part to be in form of tube, so if you apply Bernoulli's principle in this section, it will be P1 plus half rho V1 plus rho G H1 is equals to P2 plus half rho V2 and rho G H minus H. On solving, you will get velocity of efflux is equals to root 2gh, which is similar to velocity of a free falling body under the effect of gravity from same height. So from this part, you'll be asked if this entire system is dropped under free fall. So what will be velocity of liquid, or what will be velocity of ejecting liquid? Samaira, if this entire tank is falling under effect of gravity, so what will be velocity of efflux?
It will be equal to this only.
Just tell me, what will be the net acceleration of any freely falling body? Suppose this is any system. If it is going upward with some acceleration A, if there is a block at this point, so initially, if there is no acceleration of system, it must be experiencing a downward force due to gravity, that is mg. Now, since this is accelerating, so due to acceleration of system, a force will develop into it in just opposite direction equals to the acceleration of system due to inertia. So a force will develop into it in just opposite direction, which is equals to mass times acceleration. This force is called pseudo force. It arises due to acceleration of system. So in this case, net force will be mass times g plus a, or you can say net acceleration will be g plus a. Similarly, while going down, net acceleration becomes g minus a, and under free fall, net acceleration becomes 0. Is it clear?
Yes, sir.
So if you drop this particular tank under free fall, net acceleration will become 0. So if you put net acceleration in this part, velocity of ejecting liquid will be 0. It means there will be no ejection of liquid under free fall. Is it clear?
Yes, sir.
In case of free fall, net acceleration will be 0. So velocity of ejecting liquid will be 0. Arslan, any doubt? Next is, let's say liquid is ejecting out at some velocity VE. So it will fall at this particular distance. So from this part, we may define its range, its time of flight from this height, h minus h. So time of flight will be root under 2h by g, and range will be product of velocity and time of flight. So it will be root under h times h minus h. So Myra, just tell me at which point holes should be cut out to have maximum range? It should be at bottommost point or the topmost point.
The bottom.
Okay. Suppose if you made this particular hole at the bottom point, so h minus h will become 0. Is it clear?
Yes.
So if you put in this expression, time period will be 0. So it means range will be 0 in that case. But suppose if you made this particular hole at the highest point, so small h will be 0, so velocity of ejecting liquid will be 0. So in that case also, the range of liquid will be 0. So if you differentiate this particular expression, I define your mathematical physics or mathematical tool if you have to get maximum or minimum value of a particular function. Just differentiate that particular function and put it equals to 0. In this part, we have R range for which we have to maximize it. It is depending upon small h, which is variable in this part. So if you differentiate it and put it to 0, you will get small h is equals to capital H by 2. It means at the midpoint of tank, if you cut the hole, you will get maximum range. And R maximum will be equals to level of liquid up to which it is fed. Samira, is it clear?
Yes, sir.
Let me derive this particular part. According to relation, range is equals to 2 times under root. We may write this particular part as power half. And if you multiply this term, you will get h into h minus h squared. In this part, we have two different functions. One is exponential and the other is algebraic. So dr over dh, 2 being constant, differentiation of exponent. So it will be n x to the power n minus 1. Further, differentiation of algebraic function, h being constant, small h having differentiation 1 minus h squared, so its differentiation will be 2h. If we equate it to 0, this entire term having negative exponential will be in denominator. So if you move this part to right side, so you'll get 0. So you're left with just h minus 2h is equals to 0, or simply h is equals to h by 2. It means holes should be met at the midpoint of tank to have maximum range. Is it clear now?
Yes.
Okay. Now you'll be given, suppose the level of liquid in tank is up to 4 meter, 2 meter. So at what point a hole should be cut out to have maximum range? So you'll say it will be at midpoint. So according to the measurement, just divided by 2, you'll get position of hole. Next is I define you some different part related to application of this Bernoulli's principle. One is Magnus effect. Suppose you have football, and if you dropped it vertically, first without spinning, so it will go straight like this. In second case, suppose if you spin this particular ball along this direction, that is in anti-clockwise direction. So will it deviate from its actual path, or it will go straight? Samira, what will happen if you spin this particular ball in anti-clockwise direction? In this part, suppose if it is spinning in anti-clockwise direction, air around it must be going opposite to it like this. So in this part, since velocity of these two different terms will be in same direction, so it will increase. And at this point, since these two are in opposite direction, so velocity will decrease. According to Bernoulli's principle, if at a particular point velocity increases, so pressure must decreases. And at this point, if velocity decreases, so pressure must increases. Now, this velocity difference would create a pressure difference at these two different ends. And this particular pressure difference will be responsible to deviate this particular ball from its actual trajectory. Since we have higher pressure towards this side and lower pressure towards this side, so it will deviate from higher pressure to lower pressure. So it will go like this. So if you drop this particular ball in this way in anti-clockwise direction from very high, so it will tend to appear to float on air like this. Samira, is it clear?
Yes, sir.
So this is all about this entire Bernoulli's principle and fluid. Okay. Any more doubt related to this entire chapter? Arslan, any doubt?
So you told we'll do questions.
These different terms will be asked in your upcoming term.
Sir, I'm talking about numerical problems.
There will be no much numerical problem in your final exam. Your paper will be, I think, First 4 questions will be 1 marker, single word, single correct answer. Next will be just 1 minute. Just see question number 14. State and prove Bernoulli's principle. Name any 2 application of this. The or part is, what do you mean by term coefficient of viscosity? State Stokes' law. Define terminal velocity and find expression for terminal velocity in case of sphere falling through viscous liquid such as glycerine. And first question is, state Pascal's law.
So from this chapter, there will be not much numerical questions.
You'll be asked numerical from thermal properties of matter, SHM, and waves. That's it. Okay.
Okay.
Numerical will be, I think, 2 or 3. This is all about this entire thermal fluid part. Next will be thermal properties of matter. In this part, first I had defined you expansion. In expansion part, we had explained linear expansion, areal expansion, volumetric expansion. So there was coefficient of expansion, alpha, beta, gamma. So first question related to this part will be to define relation between these 3 terms. Either they will ask you in just 1 marker question to define just relation or just write the relation between these 3 different terms. Or in 2 marker question, you'll be asked to derive that particular relation. Is it clear?
Yes, sir.
Tell me the relation.
Alpha is equal to beta by 2 is equal to gamma by 3.
Good. Alpha is 1-dimensional, so alpha by 1. Beta is 2-dimensional, so beta by 2. And gamma is 3-dimensional, so gamma by 3. You may write this particular expression by taking LCM of its denominator. So it will be 6 alpha, 3 beta, and 2 gamma. Next, on the basis of this part, you will be asked on the basis of bimetallic strip. I had defined you in which side it will tend to bend on increasing temperature and decreasing temperature. Next question will be about anomalous behavior of water. Could you explain what is anomalous behavior of water?
So you explain it again.
Okay. According to the relation, length will expand as L is equals to L naught alpha 1 plus alpha delta T. Similarly, area will be equals to A naught 1 plus beta delta T, and volume will equals to V naught 1 plus gamma delta T. And similarly, density will be equals to rho naught 1 minus gamma delta T. In this part, if you increase yes, Shravya. In this part, if you increase temperature, so according to this relation, volume of body will expand and consequently density of body will decrease. But in case of water, between 0 degree to 4 degrees Celsius, only in this range, on increasing temperature from 0 to 4, volume will decrease and density will increase. So if you plot variation of this part, so from 0 degree to 4 degrees Celsius, it will be decreasing and then increasing. So it will be minimum at 4 degrees Celsius. And consequently, for density, rho versus T, at the 0 degrees Celsius, it will have lesser density. So it will rise up to 4 degrees Celsius, and further, it will decrease. So density of water will be maximum at 4 degrees Celsius. This is uneven behavior of water or exceptional behavior of water as compared to rest of the whole different matter. That's why it is called anomalous behavior, only between the range 0 degree to 4 degrees Celsius. Samaira, is it clear?
Yes, sir.
So you'll say in between 0 degree to 4 degrees Celsius, volume of water start decreasing and density start increasing, which is just in opposite nature as compared to the rest of the body. That's why it is called anomalous behavior. Next is you will be asked to define a term triple point. If you will be asked to define melting point and boiling point, you will say melting point is the temperature at which ice start melting at normal atmospheric pressure, that is 1 atm. But what will happen on melting point and boiling point if you change the pressure of system? Will there be any change or not? So let me define you. Suppose ice is initially at 0 degrees Celsius, that is 273.15 Kelvin. So I'm somehow trying to keep ice to be remain in ice by changing pressure up to a particular extent. Similarly, for vapor, and similarly in case of water. So at this point, it is about 273.16 Kelvin. In terms of Celsius, it is 0.01 degrees Celsius. And pressure for this is 4.58 mm of Hg, which is about 611.2 Pascal. At this pressure and temperature, all three states of water coexist together. It means ice, water, and vapor coexist together in this particular condition. This is called triple point. Is it clear?
Yes.
And particular temperature and pressure, if all three states of a matter coexist together, this is called triple point. Next is, there is one more term which is called regulation. Suppose you will be asked how a skate man will be able to slide on surface of ice. So let me define you. Suppose this is skateboard placed on the surface of ice. And if there is individual on this skateboard, so due to weight of this individual, there will be some pressure exerting just behind this particular skateboard. And on increasing pressure, temperature of just below surface also increases. Due to increase in temperature, ice below this particular skateboard start melting into water. And then water will act as lubrication or will be capable to slide this particular skateboard on its surface easily. Now, on getting shifted, this particular ice core skateboard slightly at some new point, the melted water, due to its surrounding temperature, that is ice, it again refreezes into water. This entire process is called regulation. Is it clear?
So can you repeat the last part?
First, due to weight of this particular individual body, pressure increases just behind this. Due to increase in pressure, temperature increases, and due to increase in temperature, ice at this point start to melt. Melting water provide lubrication or lesser friction for its movement. Now, on shifting from this point to this point, melted water in contact with surrounding ice again refreezes into ice. This entire process is called regulation. Is it clear?
Yes.
This question may be asked in some other way also. Suppose you have snow, and if you crushed it into bowl, so on applying pressure, temperature increases, so some of ice would melt, and further it will become hard sphere in shape. Why? So you'll say initially Due to pressure of a bound, temperature increases. So some ice would melt into water and they will acquire spherical in shape. Further, the surrounded ice will refreezes water into ice so that they become rigid or solid sphere or a spherical bow. This is another example of regulation. Is it clear?
Yes, sir.
So this is all about the first part of this thermal properties of matter. There will be another question, just 1 minute. Let me just show you. Just read question number 11. Blacksmith fixes iron ring on the rim of wooden wheel of a bullock cart. The diameter of the rim and the iron ring are 5.243 meter and 5.231 meter. It means iron ring is smaller in diameter as compared to the wooden rim. So iron rim must have to expand by increasing temperature. Let's say initial temperature is 27 degrees Celsius. So to what temperature should the ring be heated so as to fit the rim of the wheel if alpha is 1.2 in 10 to the power minus 15? Try to solve this part. We have initially length of or diameter of a ring, which is 5.231 meter. It has to fix on wooden rim, which is 5.243 meter. So it will act as final diameter and it will act as initial diameter. Coefficient of expansion is 1.2 into 10 to the power minus 5 degrees Celsius or per Kelvin. So according to the formula, we have to calculate final temperature. This entire thing is at some initial temperature 27 degrees Celsius. According to the formula, alpha is equals to delta L. In this part, we can write delta D divided by initial D with change in temperature delta T. So delta T is equals to delta D divided by D naught times alpha. Delta T is final temperature minus initial temperature. Delta D is change in diameter. So just subtract these two parts. So it will be about 0.012 divided by initial diameter 5.231 times alpha 1.2 into 10 to the power minus 5. On solving, you will get final T. Samaira, is it clear?
Yes, sir.
Shravya, any doubt? Okay. One more question. Just read question number 2. First, we have, what do you mean by triple point of water? Which I just explained you. And next, why a small gap is left between the rail of iron rail of railway track. Samira, just explain. Any idea? It means suppose you have one of the rail or railway track, and at junction or at joint, there will be some gap left over like this. You will say, since this is composed of any metal, so on changing temperature due to seasonal change, length will change or length will expand in summer. So on expansion, it will acquire up to this part, and similarly, it will acquire up to this part. That's why there will be left gap in between two rails, so that on changing temperature, it will expand to acquire that particular gap or fill this particular gap. Samaira, is it clear? Okay, so this is all about the first part, that is expansion. Next is calorimetry, in which you'll be asked any numerical related to that part. In calorimetry, I define you heat, which is responsible for two different parts. First, to change state of matter, that was latent heat, latent heat of fusion, or latent heat of vaporization. And the second, heat, which causes to change the temperature of substance. So it will be specific heat. So mainly in calorimetry, we may define two different heat. First is Q is equals to ms delta T, and second is for change of state, it will be Q is equals to M times L. L is latent heat of fusion constant or latent heat of vaporization constant. For the calculation of these type of problem, first try to draw graph related to that process, and for each different step, you will get amount of heat required or released during the process. Let me just ask you a question. Find amount of heat released in changing water at 10 degrees Celsius to ice at minus 20 degrees Celsius. So in this part, let me just show you a graph related for this particular conversion. Initially, we have water in liquid state at 10 degrees Celsius. So it will cool down to 0 degrees Celsius and still remain in liquid state. Further, at this point, to change its state, heat release will be equal to latent heat. And next, to further cool it down to minus 10 degrees Celsius, so it will be specific heat. Samaira, is it clear?
Yes, sir.
Initially, we have water at this point, which is plus 10 degrees Celsius. So it will cool down from this point to 0 degrees Celsius and still in water. So this heat released will be in terms of specific heat, Q1. On changing from this point to this point to form ice, it will be change of state. So it will be latent heat of fusion, and further to cool it down to minus 20 degrees Celsius. So it will be specific heat. For first part, mass of water, specific heat capacity of water, change in temperature, 10 minus 0. For second part, mass of water to be freezes, time latent heat of fusion constant, and Q3 is change in temperature of ice from 0 degrees Celsius to minus 20 degrees Celsius. So it will be mass of water. Now it has changed into ice, so it will be same. Specific capacity of ice times change in temperature, 20 degrees Celsius. So Myra, just tell me the value of specific heat capacity of water.
It's
Latent. Yes.
1 calorie per gram.
Good. 1 calorie per gram per Kelvin. Latent heat of fusion constant.
80 grams per gram.
80 calorie per gram. And similarly, specific capacity of ice, it will be 0.5 calorie per gram. Just substitute these values and sum up all this term, you'll get total amount of heat released during this process. So first, for this entire part, for calorimetry, draw the phasor curve related to temperature and heat. And on the basis of each different process, you'll get heat, that is, it is specific or latent. On the basis of it, we may define. Shravya, any doubt? Okay, so this is all about this entire part, that is calorimetry part. Let me just ask you a question. You'll be asked, in waterfall, why the temperature of bottom water is slightly greater as compared to the above water? Samira, could you explain? Suppose in waterfall, water is falling from any height, this. Up to this part. So on falling from this point to this point, or due to this height, or change in its height, there will be change in its gravitational potential energy. So at this height, water will have higher gravitational potential energy. On falling down, gravitational potential energy decreases. So you will say this change in energy due to gravitational potential energy, mgh, it will convert, or some amount of it will convert into change in temperature, that is ms delta T. So delta T will be equals to mass gravity height divided by mass specific heat. So gravity height divided by specific heat. This quantity will be responsible to change the temperature of this bottom water slightly greater as compared to the above water. That's why in waterfall, temperature of water at the bottommost point is slightly warmer. Samira, is it clear?
Yes, sir.
Shravya? Any doubt?
No, sir.
Okay. Let's stop here for today. We'll continue the rest part of this chapter as well as thermodynamics and the very small portion of kinetic theory of gas in next class. Okay. Till then, just revise this entire term, and next class you may ask different problem related to this two chapter. Samaira, any doubt? No, your Viva will be on Tuesday. And for Viva, you will have to prepare wave. Yes, Shravya. Okay then, thank you.